Today we're going to examine symmetries and conservation laws. It's an extremely important idea in quantum mechanics, field theory, dense matter field theory, many other fields. A lot of this we have to thank the mathematician Noether for. She was the one who put forth Noether's theorem, which says that wherever we have a continuous symmetry, we also have a conservation law. So there's a one-to-one relationship. So for example, if we talk about, as we will, translational symmetry, that's associated with the conservation of linear momentum. We talk about rotational symmetry, as we will, that's associated with the conservation of angular momentum. Other things as well, when we talk about, in a more esoteric way, which we probably won't do in this course, if we talk about the conservation of charge, electric charge, that's also associated with the symmetry, but it's a gauge symmetry, and we kind of leave that notion to your courses on quantum electrodynamics and field theory. So what we want to do is examine the connection between symmetries and conservation laws in this chapter. It's rather complicated, but it's extremely fundamental in what we want to do. We're also going to look at things like energy level degeneracy. We're going to look at selection rules, which sort of tell us which transitions are allowed and which are not allowed. Let's talk about symmetry. As the word suggests, it's a transformation that leaves a system unchanged. So for example, suppose I have a square, perfect square. If I rotate that square by 90 degrees, let's just say I did, it looks the same as it did when I started. If I rotate it by less than 90, then the picture does not look the same. So what we say is that we have a symmetry that is n pi over 2, where n must be an integer. On the other hand, if I have a circle, doesn't matter how many degrees I rotate that circle, because a perfect circle is going to look the same no matter how I rotate it. So we say that we have continuous symmetry in the case of a circle. In quantum mechanics, if a Hamiltonian is unchanged by some transformation, whether it's a rotation or a translation or something else, we say that the system has a symmetry. We're going to talk about 3 operators right at the start, and then we'll delve into each of them in far more detail. So we can talk about a translation operator. Translation operator can take a function and move it by a distance a. So for example, I can say, I'll use my operator capital T of a times psi of x gives me a new function psi prime of x, which is just equal to psi of x minus a. So I've just translated the whole system by some distance a. We're going to talk about the parity operator. The parity operator in one dimension, so let's do it for one dimension first. We use capital pi for that. If I apply it to psi of x, it will reflect the function about the origin. So that will result in a psi prime of x, which looks like just psi of minus x. It's a parity operator in one dimension. If I do it in 3 dimensions, it's a bit more complicated. It's pi applied to psi of x, y, and z. That's going to give me psi of minus x, minus y, and minus z. So reflected about all 3 of my axes in that case. So that's another operator we're going to spend some time with. The Third is the rotation operator. Rotation operator, let's say we're rotating about the z-axis. And I'm going to rotate about the z-axis through some angle phi. I can say my rotation r sub z of phi applied to psi of r, theta, and phi is going to be equal to psi prime of r, theta, and phi, which I can write as psi of r, theta, and phi minus the other kind of phi, if you like. Two kinds of little phis. So those are the three basic operations we're going to be talking about, and then, of course, to talk about the symmetries associated. Let's start with the translation operator. Let's express my translation operator T of A in terms of a momentum operator. Remember I said at the start, we're going to find that translational symmetry implies a conservation of linear momentum. Let's see if that works. Let's replace psi of x minus A by its Taylor series. So I can say T applied to A, applied to psi of x would be psi of x minus A, and I'm going to write it by its Taylor series. Sum n equals 0 to infinity, 1 over n factorial minus A to the n, dn dxn psi of x. So I've replaced my translation operator, replaced my function psi of x of A, x minus A by the Taylor series. I can write that as sum n equals 0 to infinity, 1 over n factorial minus iap divided by h bar, make that to the n, times psi of x. Well, the right-hand side is just the exponential function. So I can write T of A then is just e to the minus iap over h bar. What does this mean? This means that linear momentum is said to be the generator of translations. Notice something else. It's a unitary operator. So T of A to the minus 1 is equal to T of minus A. And it's also equal to T of A dagger. Well, now the question becomes, how is it that we translate an operator? Let's address that. Suppose I have some transformed operator, Q prime, and it gives the same expectation value as the untranslated state. So Q prime gives the same expectation value for psi as the operator Q does for psi prime. In other words, the wave function in the translated state.
Let me ask you about something.
That there are two ways to calculate translation effects. One, we can shift the wave function psi over some distance, or through some distance, let's say. This is what we call an active translation. On the other hand, we could shift the coordinates, or shift the origin of the coordinates. In the opposite direction. And that's constituting a passive translation. So we're not moving the wave function, we're just moving the coordinates. So those are two ways that this can happen. Mathematically, what this is saying is that psi prime q psi prime is equal to psi q prime psi. So q prime is the operator in the shifted coordinate system. I'm going to write it like this. I'm going to write psi t dagger q t psi, of course, is equal to psi q prime psi. Notice, if t applied to some function f, some cat f, is equal to tf, it must be that I can go the other way with bra t, I should say bra f and t, and write that as f t dagger. What that tells me then is that q prime is just equal to t dagger q t. Let's do an example, a real simple example. Let's find the operator x prime. The operator would be obtained by applying a translation through a distance a to the operator x on some arbitrary function f of x. We'll call that a test function. In other words, I'm going to operate on my test function with my operator x prime. That would be equal to the Hermitian conjugate of my translation operator times my original operator times my translation operator, all applied to f of x. But since t dagger of a is equal to t of minus a, we can write x prime applied to f of x is equal to t of minus a x t of a times f of x. But also, x prime of f of x is equal to t of minus a times x times f of x minus a. In addition, t of minus a, by all this, applied to x, f of x minus a, is equal to x plus a applied to f of x. What does that mean? That means that my translation of this x prime operator applied to f of x actually translates the function. I multiply the function by x plus a, which tells me that my translation operator x prime is equal to my initial translation operator plus a. So x prime operator tends to shift the coordinates to the left by a distance a, so that the position is transformed, in transform coordinates would be greater by A than in the untransformed coordinates. Also note that T dagger applied to the momentum operator times T gives me, of course, my momentum operator. In this case, what that means is my momentum operator is unchanged as a result of space translation. The momentum operator is independent of where you place the origin, which tells me that when I have translational symmetry, I have a conservation of momentum. Let's look at that more carefully. Let's look at translational symmetry. Let's take the Hamiltonian. System's translationally invariant if the Hamiltonian's unchanged in the following transformation. So if I do a translation operating on my original Hamiltonian, and I get back my original Hamiltonian. Now, since my translation operator is unitary, I can multiply both sides of the equation by t. So if I do that, I can write this as t h t th, which tells me then that ht is equal to th. In other words, their commutator, t and h, is 0. So we can say quite definitively that we have translational symmetry as long as the Hamiltonian commutes with the translation operator. Example, suppose we have a particle of mass m moving in a one-dimensional potential. So my Hamiltonian would be p squared over 2m plus v of x. The transformed Hamiltonian, h prime, would be equal to p squared over 2m plus v of x plus a, which implies that v of x plus a must equal v of x. Well, this can happen in either of two cases. One, v of x is a constant potential, and so we have continuous translational symmetry, or v of x is a periodic potential, in which case we have discrete translational symmetry. Both of those cases, though, will give us translational symmetry. Discrete translational symmetry, though, is kind of interesting because for those who've had a solid state physics class, it gives us a very important theorem in solid state physics called Bloch's theorem. And of course, Bloch's theorem applies to periodic crystal lattices. That's where it's used. It applies to a lot of things, but that's where it's used, or was originally used in solid state physics, now condensed matter physics. If I have two operators commuting, we say that they have a simultaneous, a complete set of simultaneous eigenstates or eigenvectors. If H is a translational invariant, then the eigenstates of H are also eigenstates of the translation operator. In other words, if this is the case, H applied to psi of x gives me E psi of x, then my translation operator applied to psi of x would give me some eigenvalue lambda psi of x. But since t is unitary, its eigenvalues have magnitude 1. So lambda is going to be equal to 1. And so we're going to write lambda as, in general, some function e to the I phi for any real number phi. Typically, we write phi by convention as minus q times a, where we define h bar q as a crystal momentum. You'll learn more about this when you take the solid state physics class. Such that psi of x minus a is equal to e to the minus I qa times psi of x. Bloch's theorem says, same idea, psi of x is equal to e to the I qx u of x, where u of x is equal to u of x plus a. U of x represents a traveling wave with wavelength equal to 2 pi over q. This is Bloch's theorem. It says that stationary states of a particle in a periodic potential are periodic functions multiplied by traveling waves. So an electron in a crystal has stationary states that are traveling waves, and they are periodically modulated. Which tells me that an electron can travel through a perfect crystal without even scattering. And we can apply this to ideas or concepts like electronic conduction in solids. We can also talk about continuous translational symmetry and momentum conservation. So that was discrete. Let's talk about continuous. The system has continuous translational symmetry, then H commutes with T of A for all A, regardless. So let's consider the infinitesimal translation, T of little delta. I can write that as e to the minus I delta P over H bar, and it's equivalent to 1 minus I delta P divided by H bar, where delta is just some infinitesimal length. If I apply my commutator to the Hamiltonian and my translation, my infinitesimal translation operator, I'm applying H to 1 minus I delta P over H bar. And that's going to be equal to 0, which implies that momentum is also conserved. So if H has continuous translational symmetry, it must commute with the momentum operator. And if that's the case, what that means is the time derivative of my expectation of momentum is equal to the commutator of H and P, and of course that's going to be equal to 0, which means momentum is a constant of the motion. So you get, when I have continuous translational symmetry, that implies conservation of momentum. Again, good example of how symmetries imply conservation. We'll pick up with conservation laws in more detail next time.